Number 58. The vapor pressure of water at 40 degrees Celsius is 7.34 times 10 to the 3 newtons per meter square. Using the ideal gas law, calculate the density of water vapor in gram per cubic meter that creates a partial pressure equal to this vapor pressure. All right. So, sounds a little confusing, but let's write down the ideal gas law. What we're going to do is I'm going to use this version of the ideal gas law. PV equals nRT. PV is equal to nRT. In other words, the pressure of a certain gas multiplied by the volume of that particular gas will equal then the moles of that particular gas in the sample multiplied by the R constant multiplied then by the temperature of that gas. Now, what we are required to do is we are required to find the water vapor density, right? That's what they want us to find. They want us to find the density. So now what I need to do somehow is we can also recall, right, that density is going to be mass per volume. Now, specifically, they want the units to be gram per cubic meter. All right, so let me just write that in here. I need gram per cubic meter. These are the units I want to solve for, okay? In other words, I need to solve for mass per volume. The problem here is that I don't have a mass unit in this formula, right? I have a mole unit, but I don't have a mass unit. So this is the key critical insight, that the moles are related to mass via the molar mass, okay? So the molar mass, I'll abbreviate it MM, the molar mass of a particular molecule or an atom, depending upon what we're talking about. In this case, we're talking about water, all right? So water, remember, has the chemical formula H2O. That'll come up, that'll be handy in a second. So the general formula is that the molar mass of a particular molecule will be equal to the grams of that molecule divided by the moles of that molecule. Now, when you go to the periodic table and you find then for water, we know that within water, there exists 2 hydrogens and there exists 1 oxygen. And if each hydrogen weighs about 1 gram per mole. I mean, that's what happened when you go to the table, right? You see hydrogen over here, you got your atomic number, and then you have your mass number up here, whatever, right? Or your average atomic mass, I should say. It's about 1.000, whatever, 8 or something. Just use 1, right? It's close enough. So I know that the mass then per mole of a single hydrogen atom is going to be about 1. But since I have 2 hydrogens, I have to multiply it by 2. So I know that this will be 2 grams per mole. And then for oxygen here, when you look up oxygen on the table, it's like 15.999. I'm going to use 16. All right, close enough. So 16 for every atom of oxygen, it weighs 16 grams per mole. Since I have 1 oxygen, I'm going to multiply it by 1. And I realize I'm doing the exact opposite here. So let me write, no, I'm not. No, I'm not. So this is 16 times 1. I use the molar mass and then multiply it by the number. And then that's simply going to be equal to 16 grams per mole. And now when I add these two together, that's the whole molar mass of water. So it's 18 grams per mole. All right? So, in other words, when I look at this formula over here, I know molar mass is equal to 18, right? And then I know that this 18 will equal then gram per mole. Okay? What I want to do is I realize that the n here, and this is always part of the problem, that the variables are different. This n, remember, represents mole. So if I can solve this equation for mole, I can basically do a substitution. Okay? All I'm going to do here is just cross multiply. I'm going to switch the two. I'm going to move the mole out of the denominator on the right-hand side up into the numerator on the left, and then similarly I'm going to bring the 18 on down to where the mole is. So that would give me now mole would be equal to then gram per 18, or aka per molar mass. Now what I can do here is, again, I realize that now the mole is the same thing as this. So what I'm going to do then is I'm going to take this value and I'm going to plug it in for n here. Why am I going to do that? Again, remember the whole problem was I didn't have a, let me go to here, I didn't have a mass unit in here. I had to somehow shove in a mass unit like gram or kilogram or something like that, all right? So the way in is through the mole. So now watch. This is going to be PV is equal to gram G over 18. I could have left this as mm. It doesn't matter. Multiplied then by RT. Now, notice, right? What are the units of volume? They're cubic meters in this formula, right? And look at what I need to find. I need to find gram per cubic meter. So the whole goal here and what I'm going to solve for is I'm going to try to solve this equation for gram per volume. I know that's a little confusing because I plugged in gram here instead of mass. Right, I could have plugged in an M. Actually, why don't I do that? It might be a little easier at this point. You see how it converts. Gram is just the unit of mass, right? So let me just leave this as M for now because I think it'll make a little more sense, right? Mass per volume, that's exactly what this is over here. Okay, that's what I'm solving for. So how do I do that mathematically? All I have to do then is simply bring the V on down to here, bring the 18 on up to there, bring the RT on down, whoops, to there, right? These are all just cross multiplications. I'm just shifting some things around. And lo and behold, here it is. I'll just rearrange it and look, there it is. This is the formula, okay? So now it says that the mass per volume, which by the way is, remember, I was using grams here. That's what comes from the periodic table, gram per mole. So I know that these units here will represent grams per cubic meter. And that's what I want to solve for. So now all I need to do is plug in the values. So the pressure here is 7.34 times 10 to the third. That's what was given, times the molar mass of 18, all divided by then the R constant of 8.31, then multiplied by the temperature. And they said 40 degrees Celsius, but you know we can't use Celsius, right? We have to add then 273 to convert that into Kelvin. And why don't we take out the calculator and see what it comes out to be? So 7.34 times 10 to the third multiplied by 18, divided then by 8.31 times then 40, and let me do parenthesis again, 40 plus 273, and we get 50.8 or so, right? It seems to be. So here, let's write this down. So this is about 50, so I get 50.8, and this will now be gram per cubic meter, right? And this is equal to the mass per volume. So now notice, on the table, it says the result should be the same. Okay, so then it says at the bottom, the result should be the same as the saturation vapor density at that temperature, so 51.1 gram per cubic meter. Here I got 50.8, so one of two things is possible here. Either I plugged a value in wrong, so let me just double check. So I got 7.34 times 10 to the third, times then 18, divided by then 8.31. You know, everything looks good. Yeah, so one of two things could, probably where the error is remember I was rounding over here with the molar mass. So possibly if I used the exact molar masses, I would have been a little closer, right, to the exact answer there. You know, but however, this is close enough. This is, please do not be concerned with this. All right, this is totally close enough. If you wanted to find the percent that I'm off, subtract the two. Take 51.1 minus then 50.8, then divide it. You can divide it by then the average because that's really the easiest way to do it. But just divide it essentially by 51, and we have a 0.5 or 0.6% difference. All right, it's insignificant. So guys, hopefully this helps. All right, please remember to help us out and subscribe. We'll see you next time. Take care.